Good morning, good afternoon, and good evening to all of our attendees joining us today for this latest Data Science Central webinar. This is Bill Voorhees, your host. I'm the Editorial Director with Data Science Central and also Chief Data Scientist for Data Magnum. I'd like to start off our event today by thanking Dell Statistica for sponsoring today's event. Statistica is an integral supporter of the Data Science Central community, and we're honored to have them sponsoring our event today. I'd also like to take this opportunity to mention and show our appreciation for some other recent sponsors, including Tableau, IBM, Alteryx, Teradata, Crowdflower, Exaptive, and Cubal, to name just a few. Now, past webinars are available on demand at datasciencecentral.com, and if you haven't had an opportunity to take a look at them, I encourage you to do that. They provide some very useful insight into a wide variety of topics of interest to our data science community. Today's webinar is entitled, What Does IoT Edge Analytics Look Like? And before we begin, I'd like to briefly review the format of today's webinar. Today's event will be an hour long. We'll have two presenters that I'll introduce in just a minute. There'll be a 10 to 15 minute Q&A following the presentation, and this event is being recorded and will be available on datasciencecentral.com later this afternoon following today's live event. I'd also like to encourage our attendees to provide questions throughout the presentation. We'll be reviewing and presenting them on your behalf during the Q&A portion of today's event. Well, I'm very pleased to introduce today's speakers, Jeremy Melville and David Sweener of Dell Statistica. Now, Jeremy Melville is a senior data scientist at Dell Statistica and has been helping companies implement predictive analytics in their organizations over the past 20 years. He has experience in multiple industries and domains, including finance, telecommunications, marketing, retail, and healthcare, to name just a few. And he believes that all organizations can benefit from analytics regardless of their domain. David Sweener has close to 20 years of business analytic experience, spanning product marketing, strategy, product development, BI and advanced analytics, data warehousing, and manufacturing. In his current role as the Global Analytics Product Manager for Dell Statistica, David's responsible for technology, marketing, and go-to-market strategy for the Statistica Analytics portfolio. Now, prior to joining Dell Statistica, David worked at SAS Institute as a product marketing manager, specializing in competitive intelligence, collaborating closely with organizational strategy teams on competitive differentiation. And before that, he served in a variety of roles, including semiconductor yield characterization, data warehousing, and advanced analytics, and was part of the Business Analytics Center of Competency for IBM. David holds a Bachelor of Science in Applied Physics from Rensselaer Polytechnic in Troy, New York, and an MBA from the University of Vermont. Well, thanks for being with us today, Jeremy and David. We're looking forward to your presentation. Today's webinar showcases the new Statistica features around edge scoring for IoT analytics and native distributed analytics architecture, NDAA. Today's webinar will also demonstrate deploying advanced analytics onto any edge device or IoT gateway and running analytic workflows at the edge of the network to transport predictive results. Discover NDAA that will enable you to build workflows and train and run models completely within your database engines without transporting data out of your big data systems. So today you'll learn how to deploy analytics onto the edge of the network, reduce the need to transfer large data streams over the network, build and execute advanced analytics on big data systems, and carry out intensive computations with all data in every source system, including Hadoop clusters, database appliances, and other high-performance platforms. David, with that, I'm going to turn it over to you. You can begin as soon as you're ready to go.
Okay. Thank you for that warm introduction, Bill. I'm just thrilled to be here with Jeremy Melville, and we're both really excited to see, so many people take a few minutes out of the day to discuss IoT Edge Analytics and really see a demo of Dell Statistica's capability within the IoT space. As you mentioned, I got my start in the semiconductor industry doing analytics, BI, and data warehousing, and if you can imagine, it's probably one of the most complex environments out there. So I am happy to be the product marketing manager now for Dell Statistica, and that is one of the industry-leading analytics platforms on the market. Jeremy?
Thanks for the intro. As was mentioned before, I'm a data scientist with Dell Statistica with over 20 years of experience. And today I'll be showing you a bit of a demonstration, as we've just discussed, about Edge Analytics, being able to build, train models in big data systems, as well as deploy models onto the edge of the network, so that is onto gateways or IoT sensors themselves. We'll also be first of all, we'll be talking a little bit about the value of algorithms and big data, and getting into using Statistica as the way that we're going to be demonstrating. There are many tools out there that we can use, and Statistica is one of the tools that we'll be using today.
All right, perfect. So, what I'm really excited to hear, when you look at the Internet of Things, there's a lot of estimates out there, but one of the most astounding ones to me is it says by, 2020, there's going to be over 50 billion things that are out there to be managed. These include homes, cars, utilities, and these are all connected to one another and, through the Internet and sensors. They say that it will contribute about $15 trillion to the GDP. There's going to be over 100 million light bulbs, just simple light bulbs connected to the Internet, and that the people that are doing development, within the Internet of Things ecosystem, there's around 300,000 today, and that's expected to rise to about 4.5 million in 2020. So I really think that the algorithms define action, and the IoT is really going to bring about sentient tools. So when you look at the 50 billion connected devices, 17% of them are going to be computers, so PCs, smartphones, tablets, etc., and 83% of them will be devices. So these are sensors, and they will be embedded in smart appliances. And what is enabling this is there will be a 5G network, which is 10x faster than today. There will be more Internet IP addresses with IPv6, and one of the key components to this is that the sensor prices are dropping. Today, sensors run about 60 cents, and they're expected to drop by 5%. So that's 2x the previous rate for the next 5 years. So within the Internet of Things, I really think it's the algorithms that turn actions and impact the customer. And there's a lot of security and privacy concerns. We're not going to touch on that. We're going to stick to the algorithmic portion of it for today. So when we look at the analytics of things, there's no question in my mind that IoT will be transformative. If we look at the automotive market, for example, there's going to be a lot of new data sources out there. So, for instance, the car itself, there's connected car data. That could be network data and contextual data. If you're an OEM or dealership, you'll have access to better real-time vehicle diagnostics, in-car service consumption. If you're an insurance company, perhaps there's aggregated and anonymized driving data. There's incident data. If you're a fleet, you own a bank of trucks, perhaps there's performance data you compare against the competition. If you're a federal or state government agency, you might have access to breakdown data, accident data, environmental data. Smart cities, real-time traffic flow, incident alert, parking. If you're an advertiser, what can you know about the customer and passenger demographics, and then B2B, content usage, frequency, and length. So just picking one of these industry here, there's a lot of exciting possibilities and new business models that will arise with the Internet of Things. Jeremy, do you want to comment on one?
Yeah, certainly. We can certainly go over a lot of these use cases in more detail in the Q&A session at the end. But just to state here that dynamic algorithms are really at the core of new customer interactions. And David, you just mentioned smart cities, and people are familiar with things like the Waze algorithm, being able to direct thousands of independent cars on the roads to reduce congestion. In finance, we can do location-based algorithms to provide personalized experience at bank branches. And if we talk about healthcare, for example, patients can receive real-time personalized and optimized care in operating theaters using live surgery data combined with patient records. I think IoT is still in its infancy, but there are a number of quite impactful use cases that are coming out today already. I'll just jump to the next slide, I think, David.
Okay, so so there's no question. I think there's going to be entirely new business models. We think that the IoT is in its infancy, and it is going to be transformative. We're not going to read all of these industries here, but this is just a snapshot that came from an analyst report that people are seeing opportunity for process improvements or innovation, and I think entirely new business models are going to be developed. If we think about these 50 billion devices that are out there, one of our customers, Sanofi, they're a huge pharmaceutical manufacturing company, and they were quoted in Forbes as saying they have been doing the Internet of Things for over 20 years. They have 112 plants worldwide, and today, 70,000 sensors, and 3 of them have been linked up, and teams, evaluate over 100 million data points per day. And one of the things that they talk about is the compression of time. So really, that's the time between when the data is available and when they can act in it. So really, I think the Internet of Things is going to help us reduce the time it is to react. And the traditional way of doing things is you would take all this data, you would aggregate it, amalgamate it, move it to a centralized server, and you do analysis on that, and then you would push that decision result back out to the operator or someone in the plant. And I think I'll set that up, for Jeremy. I think there's a better way of doing things, and that's what we want to talk about today. Jeremy?
Great. So if you see this slide, it's an example topology of the Internet of Things and Edge Analytics. In traditional Internet of Things, most sensor data would be transported across the network to some type of data center, and then the analytics would be conducted in a central location. What we're talking about today is being able to transport the analytics closer to where the data are generated. So that is being able to execute the analytics on either the sensor devices, if they have some type of operating system and are capable of running a process. Certain sensors wouldn't have an operating system, for example, like a light bulb. So we would execute analytics on the gateway or close to the gateway. So we have the ability then to execute the analytics on the gateway, taking in the raw data and only transporting the aggregated or the calculated results back to the data center for further core analytics, further analytics on the data. And I'd also like to introduce the concept here of native distributed analytics architecture, bit of a mouthful, NDAA. Really, this is the core concept behind IoT and Edge Analytics. And in my mind, there are really 3 things that we must have to achieve this. One is the ability to build, monitor, and manage the distributed models and workflows. So in some type of most likely central location, being able to build and train models in big data systems, or taking samples of data, whichever is most appropriate, and then exporting the models and generating the code that can be executed at the data location. So I'll be showing you today how we can achieve this through Statistica. In Statistica, we can export models as a lot of different types of code bases that can be executed on different systems. And the third item is really the ability to distribute the code to internet-connected devices. So using some type of analytic transport mechanism to transport the code onto the sensors or devices themselves or onto the Dell gateway. So this is what we'll be covering today in the demonstration. So before we get into the demonstration, would you like to speak a little bit about this, Dave?
Sure. So I tend to look at any problem, there's three aspects to it. There's a people, there's a process, and there's a technology component. So the demo today is going to focus really on the technology component. But, as everybody on this call is probably aware, you can't not read something about the shortage of data scientists or statisticians out there. And there's this concept of the citizen data scientists, and maybe in the past you would have called them business analysts, or these are people that use math to do their job, but they're not trained statisticians, so to speak. And so I just want to mention to everybody out there, we have technology that allows you, within the Statistica platform to create reusable workflows to mass complexity from your citizen data scientists and create these Lego blocks so you can build very complex analytic workflows, distribute, share, and reuse them within your organization. With that, Jeremy, I'll hand it over to you.
Okay. I will start my screen sharing, and let me know when you can see the screen. So today I'm going to be using a use case around airport body scanners. And airport body scanners, you may have used used them before yourself, traveling through the airport. They're used in almost all international airports around the world, on just about every continent. It uses a radio frequency technology to detect different items, metallic and non-metallic material that may be under clothing. You've probably gone through the scanners yourself, and you put your hands up over your head, and it takes a body scan. So the issue here with this scanner is that it contains a very expensive part, a scanning tube. And the scanning tube can many hundreds of thousands of dollars, and most airports have these scanning tubes in storage, and they have them sitting there, and there's a shelf life. So if the scanning tubes are not used, then they need to be replaced, and you can imagine, how much money that really goes to waste. So what we are doing here is being able to apply analytics which are run on the scanners themselves, so on the operating systems on the scanners, to detect this machine part failure. So we can do a number of things. We can estimate the number of days to failure. So that's getting an idea of the likelihood of failure when it's going to happen, and then we're able to pre-order this expensive part at the right time. We're also able to actively monitor scanners for different conditions that increase the likelihood of failure. That is, different combinations of variables and different combinations of factors that are likely to indicate a higher risk of failure. So when a machine is more at risk of the part failing. The idea is that this dashboard here would be available in a central operations office in the US. We have the TSA agents often have a room where they're monitoring the airport. So we can also apply different types of analytics, including staff optimization. So increasing the customer service, the passenger service of and decreasing the amount of wait time. So allocating staff according to expected demand and responding to the actual demand as well. So what I'm showing here today, this is for those of you interested, this is the Statistica. This is a Statistica FIC client, the user interface, and this is the dashboard capabilities. We can see here that we are monitoring in an airport view, monitoring the different entry points around the airport, and we have red, green, amber warning lights depending on the different statuses of the entry points around the airport. So we can then go into the different entry points and look at the different staffing levels, what our estimated demand may be, and the current traffic that we're experiencing around the different entry points. You see the different entry points have either optimal staffing levels or they're overstaffed or understaffed, and the TSA agents can be reassigned to those different entry points depending on demand. So this is taking a lot of different types of data such as flight schedules, delays, weather conditions, seasonality, etc. But the interesting part, and particularly with IoT, is being able to actively monitor the different variables that are generated by the sensor device. So this is the airport scanner. Using predictive models, we are able to determine the important variables and combinations of variables that go into predicting a higher likelihood of risk of failure. So you can see in this dashboard we have temperature sensors. We have a record of the cycles per minute. That's the number of times per minute that the passengers are scanned. And we can also see things like humidity and other environmental factors that come into it. And based on all these factors, we get risk predictions, which increase the likelihood of failure. And this is an accelerated time frame here, but we can see here that there are conditions where we have high risk of failure, and we can take preventative actions based on that. So the preventative actions could be turning the machine off for a little while, or sending someone in maintenance to figure out perhaps why the temperature is so high in the scanner. So what I'll do is go through the process of the modeling, then deployment of the modeling, and the distribution of the models to the devices. Just talking a little bit about the modeling here, we have this is an output of a tree model, just to give you an idea of the type of models we're dealing with today. You can see here we're building up these rules. It looks like the cycles per minute may be the biggest factor determinant of the part failure. And then we have things like the change in temperature if it's over, change in temperature is over 2.5 22.7, then we have a higher likelihood of failure. And we can also look overall on the different types of scanners, and we can perform perhaps do some survival analysis where we can see the overall proportion of failure over time. And for each of the scanners, we can see, as an example, that this particular scanner has about a 30-day, about 30 days, we're predicting that this is likely to fail, this machine part. So it might be a good idea at this stage to order a replacement part for this particular scanner. I'll go into the actual modeling itself, and the modeling. The modeling is pretty straightforward, and you know, lots of tools out here that do this. I'll show you how we can do this in Statistica. So we start off with a data set here. We have a set of variables, and this is a supervised learning method. So we have a target, which is whether this part has failed or not. We have a number of other variables that could be factors in influencing whether this machine part is likely to fail. We then have splitting the data up into training and test samples. I'm running a feature selection, which can also show me some of the important variables. The cycles per minute, the amount this scanner is being used is perhaps the highest determinant. And then we're running 3 different models together side by side. And through different model evaluation, we can look at things like our error rates and determine and different lift charts, etc., to determine the best performing model. Now this can be this model building. The example I'm showing you here is taking a sample of data, but we can also do in-database analytics where we are running this entire workflow within the big data system. So if you have data already in Hadoop or Teradata, for example, then we can run this entire workflow in the modeling within the big data systems without having to take the data out of the systems to your analytics. So let's say we are happy with a particular model. We can deploy model to our enterprise platform. So we have a platform that stores all the models and the workflows here. We can then, as part of the second point I raised before about generating code, we can also generate a lot of different types of code to be able to be deployed to a different system. So you can see here we have, for example, C++, or it could be Java, Java MapReduce, Teradata code, etc. So that's the ability to generate the code that can be executed at the data location. And the third point was also the ability to distribute the code to the internet-connected devices. So we have here in Statistica a a RESTful API web service, which queries the enterprise system, the enterprise database. And we can see here a list of all the models that we have generated on our system. So the system that we were just updating then was this scanner cart model. So I can look at the actual code, and the code is then available to me in through a web service. So the sensors and the gateway, for example, can query the web service to get the model code, and the model code can then be executed onto the internet, on the internet connected devices. This way, if there's a change to our model, we can centrally manage any changes with version control, etc. We can monitor the health of models, etc. And we can update the models, and those updates would immediately be available to the internet connected devices. So you may also ask, how do we then distribute the code to the internet connected devices? So what we at Dell, we have a system, an application called Dell Boomi. Dell Boomi is a data transportation and transformation tool. It's a cloud enterprise cloud data transformation and transportation system. With Dell Boomi, it allows us to set up processes which may grab different data sources from different locations, map those data sources together into a single view of our data. In this example, we are grabbing the scanner data. We are also merging in some of the external environmental factors, such as the airport temperatures, mapping those together, and then we're executing the risk algorithm, and this shape here will query the web service that I had just showed you to get the model data and embed the model within this entire workflow. So we can do any data transformation type features, functionality there, and then execute the model onto these shapes. I'll go into the actual operation here. So we want to grab, what I'll do is import this, and I'll import it from my laptop. So this entire workflow is deployed onto those devices into what Boomi calls an atom. We create a connection here. I'll specify connection, and then I'll do a filter here saying anything starting with S I want to return. And what that does is it queries the RESTful API from the Statistica enterprise platform. And here's a list of all the models I have deployed. And this is the model I just updated. And it will create a profile, a request and response profile. I'll show you here, for example. So the request profile will contain the input parameters or the input variables into our model. And the output profile will give us the risk probability of failure. So So I went through with Statistica, going through building the model. So that's being able to build, monitor, and manage the distributed models, being able to generate the code, and we generate the code through a web service that can be accessed by the scanners, or in this case, we are accessing the model code using this Boomi process. This entire process is distributed, deployed onto the devices, in this case the airport scanners, and this is run, and only the predicted results will be returned over the wire. So there's no need to transport a lot of the raw data over the network. Okay, so I will hand it back to you, Dave, just to sum up, if that's okay.
Sure, Jeremy. Thank you. And one of the things that's a requirement for the Internet of Things is the Internet to be functional, and it is non-functional at my house right now, Jeremy. So if you could advance the slides to the case study one, I'd appreciate it. So for, I picked these 3 case studies out here, and we have a lot of them, but, one, is really Telenor. I wanted to start with that, and that what they're using here is they're taking cell phone data, and they're in regions where traditional credit bureaus are unavailable. They're distributing analytics across geographies, across countries, and so I think that's a really interesting case, and it goes to the testament. It shows that this analytics platform, you can manage and distribute analytics anywhere in the world. The next one, Genzyme, I mentioned they had 70,000 sensors and 100 million points of data, and that's very complex streaming data, and that's really, they're empowering their engineers to make smarter decisions in their manufacturing processes. And then the last one, Cisco, this is I alluded to this people, process, and technology, but our champion there, he had a process that took him approximately 9 months to do a proof of concept, and after he nailed this people, process, and technology, he reduced that cycle time from 9 months to 1 day, and our technology was a component of that, and some of that was these reusable building blocks, but also the flexibility to allow people to both use native algorithms within our platform as well as open source algorithms from R and Python. That. So really the key takeaways from this webcast is that I think we have a nice platform out there that really empowers the line of business users, citizen data scientists, and programmer data scientists or statisticians. The platform does address some of the broadest set of analytic use cases, including IoT Edge Analytics, and this comes from a couple very prominent analyst reports that are out there. So those aren't my marketing words, someone else's words. And then, it's a scalable platform that allows you to scale things, beyond the geography or your local environment to really deploy analytics anywhere in the world, and we collective intelligence. So with that, Bill, I'll pass it back to you for Q&A.
Well, Jeremy, David, thank you so much for that excellent presentation. We'll get started with our Q&A session. And I want to thank the audience for their participation. We've had a great many questions that have come in during the presentation, so we'll do our best to get through all of them in the time remaining. And during this Q&A session, I'll leave up this screen with contact information for Jeremy and David in case you'd like to contact them following today's webinar. So let's get started. Jeremy, David, not everybody in our audience may be completely attuned to the idea of edge analytics and IoT. Can we start with just a very brief summary of data in motion and why it is an acceptedly good idea to process data in motion at the edge of a network as opposed to deep inside it, and exactly what that means in terms of architecture so that our audience all has a common understanding to start with?
Certainly. Do you want me to take that, Dave?
Yeah, sure. Go ahead.
We alluded to the amount of the amount of data that are being generated through sensors. So when we talk about sensors, we're referring to machines that collect data, usually kind of environmental data or just say anything that is currently occurring. We have over 50 billion things to manage across the globe, and just even light bulbs and lamps, there'll be predicted to be over 100 million internet-connected wireless light bulbs and lamps worldwide by 2020. So all this data means that it requires a lot of network resources to transport great volumes of data over the network. A lot of companies are experiencing difficulties for the volume of data, not only to kind of sift through the data and determine what is relevant, but also just even the network having the ability to the capability of transporting that data. So instead of transporting those raw data across the network, we can perform some analytics where data are generated and reduce the amount of data that are transported, as well as increase the quality of the data and whatever the meaningful data may be. In addition to that, because a lot of use cases depend on a speed and real-time response, having the analytics closer to where the data are generated means that the responsiveness is a lot higher. David, do you have anything to add?
No, I think that was a perfect answer, Jeremy.
And I agree. Thank you for that excellent answer. So we deploy streaming data platforms at the edge of our networks so that we don't have to ingest all of that huge amount of fast data into our stores. Now, let me make sure that I'm clear about this, because we know that we think of Dell Statistica as a very powerful analytic platform. Now, earlier you showed a diagram that showed Statistica sitting on top of a Dell gateway, and in turn sitting on top of, I believe it was, Spark and Hive and that sort of thing. Is the Dell gateway a full streaming platform? Can it stand alone, or do I also need a platform such as Spark underneath it?
No, it can be a standalone platform as far as the gateway is concerned. The function of the gateway is to collect the sensor data and then process it, send it to a central data store. So the central data store may be Hadoop, and you may have Spark on top of that as well. But it's mainly very light processing that would be done on there. It's mainly used to transport the data.
Okay, thanks very much. Now, was interesting that you picked the example of the airport scanner, because in the world of the Internet of Things, there are a lot of industrial machines that are sufficiently complex to have their own operating systems, which I guess is true of that scanner. But a lot of items don't. My Fitbit doesn't. My light bulb doesn't. Can you help the audience understand what happens when you're not able to transmit the algorithm back to the object, and tell us what sort of operating system has to exist for the algorithm to travel all the way back to the sensor versus my Fitbit?
Certainly. So with the Dell solution and the Dell Boomi transport application, we can run those processes in a very lightweight Java virtual machine, which runs on a lot of different types of operating systems, and it has quite a minimum hardware requirement. So something like 2 gig of RAM and about 50 meg of hard disk space. However, that, of course, is not what your Fitbit would have or a light bulb would have. So depending on the device, if you have a light bulb, I just moved apartments myself. I'm setting up a connected home in my apartment, and I have a service that monitors and changes the temperature, light bulb, the security, etc. The central kind of wireless router that and application that can run within the home network, and it would be there that the analytics would take place, as opposed to on the light bulbs themselves. In the example that we gave with the Dell Gateway, and your point is very well taken, I may say, with the the smart homes and cool personal gadgets get a lot of press, but it's quite often it's the non-glamorous applications in the world of manufacturing, with factories and warehouses, etc., that get have the most traction in connected worlds. And it's those applications where you would see a lot of the analytics taking place on the factory floors, on the machines themselves, or on something like a Dell Gateway as well.
Okay, thank you for that answer. All right, so for the simple stuff, the analytics take place on the gateway, and if the sensor is smart enough and it's got an operating system, we might push that algorithm all the way out to the sensor, if we can think of something as complex as a scanner as a simple sensor, which of course it is. Now, a lot of the, obviously the creation of the new insights is taking place in the Dell Statistica analytic platform. But we also know that sensor data is notoriously dirty when it comes in, and frequently has to be combined with static data to make it richer, to be able to be analyzed. Can we do some form of data prep within the gateway to help us out?
Yes, certainly. So all the data transformation type methods we can use, calculating variables, dealing with missing data, all those things are done in combination with applying any business rules and predictive models. So all that would be encapsulated in a single process that would be run on the gateway or the device.
Right. Excellent.
Yeah.
Thank you for that answer.
David, just a comment. I think one really neat thing that we probably didn't cover very well, but we do have an embedded business rules engine within the platform, and so we talk about deploying models, but in reality is we can deploy an analytic or data prep workflow, and with this business rules engine, we can have conditional execution of other workflows or models. So if this, do this. If this condition occurs, run this. And so I think that really opens up the world. It's not just deploying a random forest or something on the edge or a data cleansing. We can really get very sophisticated with this embedded rules engine that's out there.
Yeah, I happen to think that that's a very important point. I think a lot of people think of IoT and streaming platforms in terms of very sophisticated analytics. But as you point out, as often as not, it's simply good understanding and business rules that we implement in the stream that create as much value. Now, obviously, when we're dealing in a high volume data flow, anytime we're dealing with data in motion, we want to make sure that our analytics are always up to date. And I know the thing that a lot of people miss in this IoT conversation is that the analytics actually take place in kind of the traditional batch mode within Statistica, and then are pushed back out into the stream. But obviously our ability to turn around the updates and refreshes for those models are very important. Does Statistica have a particular way that helps us accelerate refreshing those models once we've built them?
Yes, certainly. It's also important to realize that the actual calculations are not performed within the Statistica engine in this example. So what we're doing in Statistica is using Statistica to build and monitor and manage the models, but we then make that model code available as a web service. And the web service would be updated by the Statistica engine, but the IoT devices and gateways, etc., would consume that web service to query the most up-to-date and relevant models or processes, business rules, etc. So we can therefore ensure that we are getting the most up-to-date algorithms, and we still are able to manage the models, make sure they can be refreshed in response to changes in environment, etc.
Right.
And
right.
Yeah.
Excellent. Thank you. Now, as a data scientist, I really appreciate the standardization that comes with the drag and drop interfaces that Statistica has. But once in a while, I want to write my own R or Python. Does Statistica allow me to input my custom code as well as whatever Statistica generates natively?
Yes. So we can, with Statistica, you can integrate Python, R, C#, lots of different VB type code within your workflows. So we can also, in addition to embedding your code in a workflow, we can also query services such as Algorithmia, Expify, a lot of third-party services that provide modeling services. So there may be models that are published publicly, or you don't have a data science team within your organization, so you can contract out some of this work and actually remotely call a service. So Statistica welcomes a lot of third-party tools and applications, and we also have the ability to script as well in a lot of different types of languages, as well as using the user-friendly user interface.
Well, that's terrific. Thank you. Thanks for that answer. And by the way, since you raised the topic of not having data scientists on staff, how does the citizen data scientist fit into this scenario that we're talking about?
So, Dave, do you want to take that?
Sure. So, in the demo, Jeremy, he showed it had some sophisticated analytics, but it was a fairly straightforward workflow in that we had data we did some math. We wanted to pick the best model. We have some champion, challenger, and things like that, and and then deployed the workflow. So what Statistica allows us to do, if you are a data scientist like Jeremy, he can create this very complex workflow and click Save As Template. And so now, marketing guy Dave right here, I don't know what's in that workflow, but perhaps I know the inputs and outputs. So I can take these templates, and you can have any number of templates within your organization, and I put them together like building blocks. So like Legos. So I take maybe a data prep, maybe a get data, and all these different reusable templates that smarter people than myself have created on my team, and I just assemble them like Legos to build a very nice, very sophisticated Lego castle, so to speak. So this idea that we can enable reuse, allow people within organizations to create and kind of distribute and disseminate their best practices, I think it's a very interesting concept in that, we know as software vendors, as a software developer, we cannot develop everything you want to do. So what we're trying to do is provide you with a facility so you can create templates that are unique to your organization, unique to your competitive advantage, and then allow those to be within and externally your environment. If you're a partner, perhaps we have this thing called IP Protect, so you can actually obscure the template as well, the underlying guts of it, so it can't be read by anybody else, and you could actually monetize those if you so choose to.
Well, that's a very interesting feature. Thanks for pointing that out. That makes me think about some opportunities. I guess one last question. Edge computing is new. IoT has really exploded over the last year or two. Spark has caught all of our attention. Are there limitations or complexities about computing or in computing power at the edges that we need to be sensitive to, or does Dell Statistica and your gateway simply adapt to all of those issues?
There's certainly limitations, and the limitations are generally based on the type of sensor, the type of environment that you're dealing with. So depending on the operating system, the hardware that you have to work with, that will define the limitations for you. Saying that, we have a lot of interesting abilities to distribute the load across a lot of different processes. In Boomi, for example, we have the notion of a molecule. They've used this nomenclature to expand the atom idea into molecules that kind of work together. So we can expand the system, but the limitations are certainly there depending on what your operating systems and hardware capabilities are like.
Well, Jeremy, David, thanks for some great answers to some very good questions. And for those of you who asked questions that weren't answered today, we'll be sending all those unanswered questions to Jeremy and David and the Dell Statistica team so that they can follow up with you after today's webinar. Now, I have just a couple of quick announcements. If you'd please mark your calendars for October 13th. That's our next DSC webinar, which will be Accurate Anomaly Detection with Machine Learning, sponsored by Antidote. Also, I remember that today's taping will be available for on-demand viewing later today, and you can find that on the home page of Data Science Central in the Webinar tab located at the top of the page. Well, this brings today's webinar to a close, and I'd like to thank our audience for their attendance and thoughtful questions. And a special thanks again to Dell Statistica for their sponsorship, and our speakers today, Jeremy Melville and David Sweenor of Dell Statistica, for their insight into today's topic. My name's Bill Voorhees. I'm very pleased to have been your host for today's event. I look forward to seeing you all again on October 13th. Have a great day.